Okay, so today we are doing 2.5, solving a homogeneous differential equation. And I'm going to do two different types of solving. One is by substitution, okay, and the other one is going to be called a Bernoulli equation, okay. So the first one is by substitution, and when we're looking at substitution, you're trying to make it easier for yourself to solve. So what you want to use is a couple things. You're going to look at what the book is telling you if you want to use that method. I kind of like to do it this way, but it's very similar in the sense that you're still just using substitution. So you can always look to substitute y equal to some variable. I think the book uses u times x. I mean, you could use v times x. You could use any variable you want. But what you're trying to do is not use, substitute for y. You want to kind of get rid of y when you're doing these. Okay, so let's do an example here where we have x squared plus y squared. Now, if you look at the example in the book, they're just going to substitute y equal to ux into this equation. Now, what I want to do is, using this y equals to ux, is do a couple things. I want to first rearrange this differential, right? So I have dy dx equals, so I'm going to get dy over dx equals, and this is going to give me a negative x squared plus y squared over x squared minus xy, right? So the thing that I want is, if you look, right, u is going to equal, if I'm just taking this equation above, u is going to equal y over x. So I kind of want to get everything to look in the form of y over x, so that way I could do my substitution. If you have x that left over, that's okay. But you want to kind of get rid of the y's there. So I'm going to divide everything by x squared. So as long as you do that to the top and the bottom, it's okay. As long as you divide everything by x squared, it's okay. Don't just do the numerator. So if I divide everything by x squared, that first term is going to be a 1 plus y squared over x squared. And in the denominator, I would get 1 minus, if you divide this by x squared, you're just going to get y over x, like that. Now, the reason why I did that was, now I could substitute anywhere I see a y over x, I could substitute in u. Okay, before we do that though, you have to also, if you're changing the variables, think about when you did u substitution in calc, right? You still have to have something to substitute in for dy over dx, because we're changing everything to just x's and u's this time. It's almost like a u substitution in a sense, right? So you got to have a du. So here what I want is, if I'm looking at that equation u over x, I could get dy, if I take the derivative with respect to x, I'll get u plus x du over dx. So your equation will look like that. So now I can substitute everything in. So everywhere I see a y over x or some form of that, right? So like here would be u squared, here would be u, and I could also now substitute in for dy over dx. So I'll have u plus x du over dx equal to a negative 1 plus u squared all over 1 minus u, okay? Once you get it down to here where you have your substitutions, you could use one of the methods we did prior. Usually in this situation, you're going to try to separate and integrate. So let me try to get the u's together, right? So I'm going to subtract, I'm going to distribute this and subtract a u to both sides. So here now let's just simplify, right? So we have -1 minus u squared minus u times 1 minus u all over 1 minus u, right? So here, again, your algebra, just make sure you're doing okay here. So we have -1 minus u squared minus u plus u squared over 1 minus u, okay? And we then are left with the cancels cancel, so you have a -1 minus u over 1 minus u. Do not cancel that out, that is not the same thing. Now we could bring x's to one side, u's to the other side, so I'm going to have 1 minus u over, if you want to kick that negative out so it just looks neater, 1 plus u, that's fine, du. Notice I reciprocal of bringing that to the other side, and then here reciprocal of x over dx, so it's dx over x on this side. Now what we could do is we could get an easier term on this side, so we could bring that negative over. I just like the way it looks a little bit better, but you could keep the negative on that side if you want, but I think it's easier for us to do that this way. Once you get here, we have it separated, and now we can integrate, okay? We could integrate, and this side is easy, right? Because you get that negative ln of x plus c. Okay, over here, I'm going to use long division or synthetic division to simplify this, right? So think about synthetic. It should be a -1, and then your coefficients will be -1 and +1, right? So we would get a -1, and this would be a +1, so this is 2. So we wind up getting this to look like -1 plus 2 over 1 plus u du, and then that makes our life a lot easier. Where here I'm just going to get the -u plus 2 ln of 1 plus u, and then equals -ln x plus c, just like that. All right, so then from there, okay, from there we could now substitute back what we made our u. So in the beginning, if you go back up top, right, you could see that u was equal to y over x, so we could plug that back into our equation. So I have -y over x plus 2 ln 1 plus y over x equals -ln x plus c. The only other thing that maybe you could do to like clean this up, but I mean, if this is written in there and if you want to show me your work and this is what you got, I will give you credit for that. So, you know, if you're emailing me work and you get down to here and you don't know how to get into the form they want, even though I'm pretty sure they might give you this as the form anyway, all right, but what you could do is if you added, right, so say you added ln x to both sides plus ln of x to both sides, maybe you could just rewrite it like this. Oops, and then equals c. So that, you know, you might want it to just have it equal c, which is fine as well. It just depends on what you would look like. So this is substitution. And the best way to think of substitution in this sense is trying to get, in my opinion, you could do what the book does, but I like to get it into the form of, you know, y over x. So you can see how I did that here, right? Trying to get it into this form, and then it becomes easier to just substitute your u and then substitute for dy dx as well. So, you know, a couple things is you know, y equals ux or some variable x, and then get what that variable is going to equal and then try to substitute from there. Before the test, I'm going to post the test today. I'll do a couple more examples of these for you guys. Okay, thanks. All right, so let's go to Bernoulli. Okay, so Bernoulli equations, right? So when you're doing Bernoulli equations, you're gonna get you wanna get it into this form, almost like the linear form where you have function times y, but now on this side, it's gonna equal a function of x times y to some power n. All right, so for Bernoulli, what you wanna look for, always look for a y term and y to the nth, right, term. And then that'll help you set this up, okay? So in here, what you want to do is, so Bernoulli is for any n not equal to 0. Obviously that would be linear. If it was 0 and 1, you could just combine the y's together. So this is for anything greater than 1. And we're going to make our variable v equal to y to the 1 minus n. Okay, so that's how you're going to do your substitution. This is still considered a substitution method, but it's with a Bernoulli equation where you get this form. Okay, so let's do an example here. Say we have x dy dx plus y equals x squared y squared, right? So you have it look like this. So we want to kind of get it into that form that I have above, right? Can you get it to look like that Bernoulli equation? So I'm going to divide everything by x, dy over dx plus 1 over xy equals x y squared. So now I do have it in this equation, and you could see like our p of x here would be 1 over x, our q of x would be x, and then our n is 2. Okay, this you didn't have to do. You don't have to do all these steps here, but what you want to do is pick the right variable substitution. So v is going to equal y. Our n in our case is 2, so 1 minus 2, so I get v is going to equal y to the negative 1. Okay, so now let's do a couple things. We're changing y's and dy dx again. So I want to solve for y. So y is going to be equal to v to the negative 1. And if I do dy dx, right, that's going to be negative v to the negative 2. And then dv over dx. Okay, because you're taking the derivative with respect to x. So we're using all of these equations here for our substitution. So I'm going to have, let's substitute now. So negative v, negative 2, dv over dx, right? So I'm substituting in here. Plus 1 over x times y. In our case, y is v to the negative 1 equals x times v to the negative 2. I was substituting into that y squared. Okay. So if you notice now, can I get this into another form, right? Maybe I could get this into a linear form where I could divide out that y to the negative 2. If you notice, y to the negative 2 is on both sides, so that will cancel out this y to the negative 2 with this y to the negative 2, so that's nice. So I'm going to divide everything by negative y to the negative v to the negative 2. So this will give me plus 1 over x d's, and if that is, you're dividing by the negative 2, you're really adding the 2 to the variable there, which is going to give me, and it should be negative, my bad, negative 1 over x, and it's just going to be a v equals x, negative x. Okay, so all I did here was divide by negative v to the negative 2. and it gave me that. Now this is linear, you know, and you can see it's in that form that we have linear, and we go back to solving linear functions. So I want to know what is my p of x, negative 1 over x, and then that integrating factor is going to be e raised to the p of x. So e raised to the negative 1 over x dx, which is going to be e to negative ln x, which is x to the negative 1. Now I can multiply everything by that factor. So negative, not negative, what am I doing? Okay, so x to the negative 1 dv over dx minus 1 over x squared v equals negative 1. Okay. Now here you could see linear, right? Don't notice the derivative is x to the negative 1 times v. Over here we just get negative 1. Let's take our integral with respect to x. So I get x to negative 1v equals negative x plus c. And now if I divide by x to the negative 1, I will get v equals negative x squared plus cx. Okay, and there I just divided by x to the negative 1. Now remember v, right, what did we make v in the beginning, right? So v was equal to, let's go back up top, y to the negative 1, right? Y to the negative 1. And then to get y, we could just do the reciprocal, and you're left with this as a general equation or solution to that differential. So this is Bernoulli. Bernoulli is of the form that we started with, right, where you're getting it in this form, dy over dx plus p of x y equals q of x y to the end, and then looking for this as your substitution. So look for a y term, look for the y to the nth term as well, try to get it into that form, and then it's most likely going to be a linear type problem in the end. And there we go.